This locomotive operated continuously for over 50 years. It hauled the most prestigious passenger trains in the eastern United States. And in 1953, one of them drove through the floor of Washington Union Station and was repaired and returned to service. The GG1 is famous for its appearance. Raymond Loewy designed the exterior. The five-stripe gold pinstriping on Brunswick green became one of the most recognizable liveries in American railroad history. But the appearance is not why the GG1 mattered. What mattered was inside the welded carbody, an electric drivetrain so robust, so simple, and so durable that the locomotive operated for half a century and proved nearly impossible to kill. 139 units were built between 1934 and 1943. The class served the Pennsylvania Railroad, Penn Central, Amtrak, and several commuter operations. Some GG1s operated into the early 1980s, nearly 50 years after the first units entered service. This is what is inside the most durable electric locomotive in American history, and why an electric drivetrain designed in 1934 outlasted every steam and diesel locomotive of its generation. The body is beautiful. The mechanism is unkillable. By the 1930s, the Pennsylvania Railroad had electrified its busiest main line, the corridor between New York, Philadelphia, Washington, and Harrisburg. The electrification used overhead catenary wire carrying 11,000 volts of alternating current. The Pennsylvania needed a locomotive that could exploit this electrification, a high-speed, high-power passenger locomotive that could haul heavy trains at sustained speed across the corridor. The railroad tested several designs before settling on the configuration that became the GG1. The GG1 was developed through extensive testing, including wind tunnel work and a competition between prototype designs. The Pennsylvania brought in the industrial designer Raymond Loewy to refine the appearance. But the fundamental engineering was the work of the railroad's mechanical and electrical engineers and the manufacturers General Electric and Westinghouse. What they produced was an electric locomotive whose drivetrain was so well engineered that it became the backbone of Northeast Corridor passenger service for half a century. The engineering inside the GG1 is the reason it is remembered. The GG1 drew power from overhead catenary wire through a pantograph, the spring-loaded frame on the locomotive roof that maintained contact with the wire. The catenary carried 11,000 volts of alternating current at 25 hertz. The GG1 carried two pantographs, one at each end. Normally, the locomotive operated using the trailing pantograph, the one at the rear relative to the direction of travel. If the trailing pantograph was damaged, the leading pantograph could be raised. The redundancy meant a damaged pantograph rarely took a GG1 out of service. 11,000 volts was far too high to feed directly to traction motors. The GG1 used transformers to step the voltage down to levels the motors could use. The transformers were among the heaviest components in the locomotive, and they generated substantial heat under load, requiring oil cooling. The GG1 used a wheel arrangement designated 2C plus C2, two guiding axles at each end, two groups of 3 powered axles in the middle, 6 powered axles total, each carrying its own traction motor. The plus sign in the designation indicated that the 2 groups of powered axles were carried on articulated frames that could pivot relative to the carbody. The GG1's body was a single rigid carbody mounted on 2 articulated frames. Each frame carried 3 powered axles and 1 guiding axle group. The frames could pivot relative to the body, allowing the long locomotive to negotiate curves while maintaining the rigid carbody that housed the transformers and control equipment. This was the same articulation principle the big boy used, applied to an electric locomotive. Each powered axle was driven by a traction motor through a Quill drive, a system that allowed the motor to be mounted on the frame rather than directly on the axle, reducing the unsprung weight and improving the locomotive's ride quality at high speed. The Quill drive was a critical engineering choice that allowed the GG1 to operate smoothly at speeds over 100 miles per hour. The Quill drive surrounded the axle with a hollow shaft, the Quill, driven by the traction motor. The Quill connected to the driving wheels through flexible cups that accommodated the vertical movement of the axle relative to the frame. The arrangement isolated the heavy traction motor from the shocks transmitted through the wheels, protecting both the motor and the track. The combination, 6 traction motors, 12 motors in the later twin-motor configurations, the Quill drives, the articulated frames, produced a locomotive that could sustain high speed with heavy trains while riding smoothly enough to protect both the equipment and the track. The GG1 was rated at approximately 4,600 horsepower continuously, with a short-term capacity that could exceed 8,500 horsepower for acceleration. And then there is the reason the GG1 became legendary: the accident that should have destroyed one of these locomotives and didn't. On January 15, 1953, GG1 number 4876 was leading a passenger train into Washington Union Station. The train was approaching the terminal at the end of its run from Boston. As the train approached the station, the engineer attempted to apply the brakes. The brakes failed to respond adequately. A closed angle cock, a valve in the brake line, had isolated part of the train's air brake system, leaving the engineer with far less braking capability than he needed. The train was traveling at approximately 40 miles per hour and could not stop. It entered the station. It ran through the bumper at the end of the track. It crossed the station concourse, crowded with travelers preparing for the upcoming presidential inauguration. The locomotive crashed through the station master's office and came to rest with its nose broken through the concourse floor, having partially fallen into the baggage room in the basement below. The weight of the GG1 had collapsed the floor structure. By any reasonable expectation, the accident should have been catastrophic. A 230-ton locomotive traveling at 40 miles per hour through a crowded terminal. And yet, remarkably, no one was killed. The injuries, while numerous, were survivable. And then came the part that made the GG1 legendary. The locomotive was recovered from the basement. It was cut into sections to remove it from the station. It was transported back to the Pennsylvania Railroad shops, and it was rebuilt. GG1 4876 returned to revenue service. The locomotive that had crashed through the floor of Washington Union Station went back to work hauling passenger trains on the Northeast Corridor. It continued operating for decades after the accident. The accident became the defining legend of the GG1's durability. The locomotive's construction was so robust, the welded carbody, the heavy frames, the rugged drivetrain, that even a catastrophic crash could not permanently destroy it. The GG1 was, in the most literal sense, built to survive almost anything. The accident proved the GG1 could survive disaster, but the deeper proof of its engineering was how long it simply kept working. The first GG1 entered service in 1935. The design was so successful that the Pennsylvania Railroad built 139 units between 1934 and 1943. They became the backbone of Northeast Corridor passenger and freight service. The GG1 hauled the premier passenger trains of the eastern United States: the Broadway Limited, the Congressional Limited, the Senator, the trains that connected New York, Philadelphia, and Washington at the highest speeds and the highest standards of service American railroading offered. The GG1's performance came from the fundamental advantage of electric traction. Unlike steam or diesel locomotives, the GG1 did not carry its own power plant. It drew power from the catenary continuously. It could deliver enormous short-term power for acceleration, far more than its continuous rating, because the limiting factor was the electrical supply rather than an onboard engine. A GG1 could accelerate a heavy passenger train faster than any steam or diesel locomotive of its era. It could sustain high speed indefinitely as long as the catenary supplied power. And it could do this with a drivetrain that had no boiler to maintain, no diesel engine to rebuild, no complex thermodynamic system to manage. When the Pennsylvania Railroad merged into Penn Central in 1968, the GG1s continued in service under the new owner. When Penn Central collapsed and Amtrak and Conrail took over its operations in the 1970s, the GG1s continued again. The locomotives outlived the company that built them. Amtrak operated GG1s on the Northeast Corridor into the late 1970s and early 1980s. By then, the locomotives were over 40 years old. They were maintained, repaired, repainted, and kept running because they continued to perform reliably despite their age. The reason for the longevity was the fundamental simplicity of the electric drivetrain. A steam locomotive had thousands of moving parts and a boiler that required constant maintenance. A diesel locomotive had a complex internal combustion engine that required periodic rebuilding. The GG1's drivetrain was electrically simple: transformers, traction motors, control equipment, with far fewer wear points than either steam or diesel. The traction motors were rugged and long-lived. The transformers, while heavy, were reliable. The carbody and frames were built to a standard of robustness that the accident at Washington Union Station had demonstrated dramatically. The GG1 simply did not wear out the way steam and diesel locomotives did. The GG1 did not retire because it wore out. It retired because the electrical system it was built for became obsolete. The GG1 was designed for 25 Hz alternating current. As the Northeast Corridor electrification was modernized to higher frequency current, the GG1's transformers and motors became incompatible with the new system. And there was a more serious problem hidden inside the locomotive. The GG1's transformers were cooled by oil that contained polychlorinated biphenyls, PCBs. By the late 1970s, PCBs had been identified as a serious environmental and health hazard. The transformers could not legally be maintained or refilled with PCB containing oil. The combination, the obsolete electrical frequency, and the PCB contamination ended the GG1's career. The last GG1s were retired from Amtrak and commuter service in the early 1980s. The locomotive that had survived a crash through a station floor was finally stopped by chemistry and electrical frequency standards. 16 GG1s survive in preservation. They are scattered across museums and historical collections in the eastern United States, but none of them operate. The PCB contamination in the original transformers means the locomotives cannot be returned to operating condition without replacing the transformers entirely. A prohibitively expensive undertaking that no organization has completed. Every preserved GG1 is a static display. The most durable electric locomotive in American history, a machine that operated for nearly 50 years and survived an accident that destroyed the floor of a major train station, sits silent in museums because the chemistry of its cooling oil cannot be reconciled with modern environmental law. The GG1's legacy is twofold. The exterior, designed by Raymond Loewy, became one of the most celebrated examples of industrial design in transportation history. The 5-stripe pinstriping on Brunswick green is instantly recognizable to anyone familiar with American railroad history, but the engineering legacy is the drivetrain. The electric traction system inside the GG1 demonstrated that a well-designed electric locomotive could outlast every competing technology of its era. The simplicity, the durability, the robustness. These were the qualities that allowed the GG1 to operate for half a century, while steam locomotives were scrapped after 30 years and early diesels were rebuilt or retired after 20. What is under the GG1's hood is not glamorous in the way the exterior is. It is a transformer, traction motors, and control equipment. But that unglamorous drivetrain is the reason the GG1 became the most durable electric locomotive in American history. The body made it beautiful. The mechanism made it immortal, until the chemistry of its own cooling system finally brought it down. The Pennsylvania Railroad GG1 is the most durable electric locomotive in American history. Its drivetrain was so well engineered that it operated for nearly 50 years, survived a catastrophic accident, and outlived the railroad that built it. The body was a triumph of industrial design. The mechanism was a triumph of engineering durability. This is part 2 of our What's Under the Hood series. Part 1 covered the Union Pacific Big Boy and articulated steam at maximum scale. Both are linked in the description. Part 3 covers the EMDF unit in the 567 prime mover, the diesel engine that ended the steam era, not through power, but through economics. The most consequential diesel engine in American railroad history. Subscribe so you do not miss it. There is more about American railroad engineering than any single video can deliver. Each of these locomotives deserves a full mechanical study. We are working through them one at a time.